Good day, dear colleagues. I'm happy to see at the International Conference on Internet of Things. My name is Luiz Fernando Pinto de Oliveira. I'm from São Paulo in Brazil and from University of Campinas, Unicamp. And my topic today is Smart Traffic Light Controller System.
Okay, let's go. To understand the real needs of efficient semaphore deployment, it is necessary to understand what their impact on human activities. These are the main analyses to be done. Market analysis. About 68% of the world population will live in urban environments up to 2050, according to the projection of World Urbanization undertaken by United Nations in 2018. The urbanization era phenomenon that was once predominantly rural brings advantages and disadvantages to the local population. Employment availability, study, and leisure are some of the benefits generated. On the other hand, the badly planned growth of a city can cause harm to the population, such as increased vehicular traffic, congestion, increased environment and noise pollution, as well as a decrease in citizen safety. Technical analysis. According to the engineering and traffic company CT from São Paulo City in Brazil, 11% of the currents that generate signaling system inconsistency are due to the wear of the cabling and humidity, and about 13% due to external agents, such as cable theft and vandalism. According to Crank in 2014, congestion caused in the North American about 6.9 billion extra hours of travel, consuming around 3.1 billion liters of extra fuel, resulting in a borrowing cost of $160 billion. Since all traffic lights can be controlled by a central, the deployment of a strategic management plan will reduce congestion such as those caused by poor timer sizing and the lack of control to keep up with the vehicle flow daily. According to engineering and traffic company CT again, from São Paulo City in Brazil, for a complete traffic light revitalization, the city would require 2,520 km of electric cables. Because it is a semaphore system that will be communicated completely wirelessly, such occurrence would be inhibited. Ecological analysis. Successive braking and acceleration routines of vehicles result in higher emission of pollution gases into the atmosphere. According to Boris Bonsoncin, it is possible to reduce by 20% of the emission of pollution gases into the atmosphere through an improvement in the semaphore management system of urban traffic. Electronic circuit. To collaborate for traffic light system modernization and to improve living conditions in future urban centers, the present work has developed a traffic control system prototype remotely controlled using wireless communication technology. In order to provide adequate voltage levels for each circuit part, the power supply circuit shown in this figure has designed. The circuit has a power supply that converts the incoming AC voltage to the DC voltage by voltage required by the radio frequency model. For a microcontroller, a voltage regulator model for 3.3 voltage has used. In order to control DC lamps, a 12-volt DC supply voltage input terminal has been inserted to provide energy for the lamps. Microcontroller electronic circuit. Adjusting the lamp period, reading the current sensor, and the communication with the RF model are some of the microcontroller circuit performed tasks. For that, STM32 microcontroller with Cortex-M3 32-bit ARM core has used. This microcontroller has an internal real-time clock peripheral to chip. The RTC peripheral will be used as a clock source for the lamp timer's adjustment as well for the synchronization between the network semaphores. Electronic DC current sensor circuit. On way to detect the light bulb state, whether it is working normally or if it's burned, is to measure a current signal. For the particular case of DC lamp, the current sensing circuit has designed. It also allows to control the focus group via the MOSFET transistor. The burnout lamp can be detected when both the MOSFET key 1 and the BJT key 16 are blocked. Electronic AC current sensor circuit. To control and monitor AC lamps, the electronic circuit has designed. It has the same idea of burned lamps detection seen in the previous slide, but because its circuit has a AC power supply, the circuit has undergone some adjustments. The burnout lamp can be detected when the logic input level is 0 and the logic output level is 0. Network. Several wireless technologies operate under different circumstances. Similar work involving wireless semaphore communication make use of Zigbee communication protocol creating a mesh topology network. Although such protocol defines a data package delivery algorithm, it does not implement a complete routing table. The implementation of optimized data package delivery algorithm is essential for IoT applications, where most of the devices have low processing power. Developing technology from a doctorate research at Unicamp whose root algorithm is performed through mathematical modeling, allows its use in microcontrollers and embedded systems. The network block diagram, titled X-Mesh, can be seen in this figure. The N for IoT block refers to the network layer that was mathematical modeling for routes, allowing the addition of numerous devices to the network. The M for IoT block refers to the protocol layer, encrypted by means of elliptic curves. It is able to create a virtual private network for each IoT application, called Virtual Private Device Network (VPDN). This feature allows a wireless traffic light network to operate simultaneously with a wireless sensor network. In this way, the present work has chosen to use the X-Mesh network. Intersection. For the traffic light controller to be able to operate in real conditions at traffic intersection, it was necessary to search the main types of intersections. According to Joanna, the intersections that often use traffic light are chosen some on these slides. A traffic light complete cycle consists of a stage sequence. One way to display that all stages execution of all semaphores in an intersection is through a time diagram. At the operation cycle end, the same time diagram is started again, creating a traffic management plan. To perform the controller circuit tested operating at the conditions previously depicted, the experiment has carried out with the assembly of PCBs. The PCB presented in this figure allows to control and monitor a vehicle focal group with 3 lamps, a pedestrian focal group with 2 lamps, both AC and DC. In addition, it is able to perform a pedestrian button action. In order to visualize the signal sent to each VFG and PFG of each intersection, a logic analysis has used. In this test, we considered a green signal having 10 seconds and 2 seconds for the yellow signal. According to these figures, the traffic light control circuits behave as expected. The only difference is that during the practical tests, it was decided to implement the blinking red routine for pedestrians, indicating that the vehicle traffic light will turn green, according to the Brazilian Manual of Traffic Signaling. Well, the adopted microcontrolling system performed the execution of all necessary routines to establish a wireless traffic management of all semaphores in this network. The X-Mesh network proved to be feasible to manage the managed data packages through the N4IoT network layer, in addition to administrating the message exchange through the M4IoT protocol. Data collection by IoV applications, such as traffic accidents detection, shared with the proposed system, enables the enhancement of traffic light management system, blocking and creating alternative routes to not only avoid the traffic jams, but also avoid new accidents. Therefore, the designed traffic light controller circuit, besides offering a new alternative to today's traffic light control systems, allows the study and development of technologies that contribute to the transformation of large urban centers into smart cities. Thanks for listening.